Today I have the pleasure of introducing to you Einstein, who writes the probably one and only Dear Abby column for technology. I warned him that you might have provocative questions such as, I just installed Windows 7 and my computer keeps crashing. What do I do? Anyway, he's going to talk about something else, however, about science fiction and how we need science fiction today more than ever. So let's welcome him.
Thank you, Professor Levine, and thanks for introducing us to the writer. I must admit that when I got the invitation, my initial reaction was I'm not a very good fit. I'm not a computer scientist. However, for the last 20 years, I've covered the evolution of the computer industry. And I also happen to be a very avid science fiction fan. And over the course of this time, I've seen some just marvelous intersections, correlations, and confluences between science fiction and hard science. So I thought I'd talk about that today. Science fiction has been around roughly 150 years or so. Jules Verne was the first real proponent of science fiction. Science fiction writers are kind of an odd group. They tend to focus more on technology and less on stories, and for that reason, their literature is not really taken very seriously. But what they have done is they have been able to predict a lot of technology that over the course of the last century has come true. They miss as much as they hit, probably more often. So a lot of what science fiction writers come up with is just bunk, and it's not believable, and it's just gimmicks to tell the story. But there is a tremendous amount of hard science now going into science fiction. As I said, Jules Verne kind of paved the way. He was followed by H.G. Wells, one of the winners. George Orwell, Isaac Asimov, who was kind of the dean of science fiction writers in the mid 20th century. Robert Heinlein, who you may have read A Stranger in a Strange Land. Ray Bradbury and Philip K. Dick, kind of a cult author, but kind of rose to prominence the last several years because of a couple of his novels. It made a movie. Blade Runner was one of them, and Minority Report, Steven Spielberg was another. In the last generation, we've seen an increase in writers who are also scientists, physicists, astronomers, computer scientists. These include Bernard Hinge, David Brin, Gregory Benford, three of the kind of giants of science fiction in the last generation. And now we're seeing kind of an influx of kind of a British invasion. Writers like Charles Stross, Richard Morgan, Alistair Reynolds, who combine hard science with science fiction and do a very good job of it and actually tell better stories. And then, of course, there's Wayne Gibson, who I know everybody's familiar with. His 1984 novel, Neuromancer, kind of paved the way for both predicted both the internet and virtual reality and the phrase in terms of cyberspace. And there are lots of others, of course, but those are the main guys that I really like. I'd like to start with just a list of predictions in science fiction that have come true. And it's kind of fascinating. In 1867, excuse me, Jules Verne wrote From the Earth to the Moon, which was made into a very early 20th century movie. But it was fascinating because it included elements that went on to be sort of very similar to the Apollo program. The capsule that people went to the moon in was more or less the size of an Apollo spacecraft, including the lander. And when Jules Verne's astronauts came back to Earth, they splashed down. It's fascinating stuff. In 20,000 Leagues Under the Sea, Jules Verne presaged scuba gear, which wasn't invented until Jacques Cousteau came along. In War of the Worlds, remember those giant eyes that come out of the monsters from Mars and zap people? Well, that was a precursor to the laser beam. The robot, in 1920, there was a guy named Carol Capek who wrote Rossum's Universal Robots. That's where the term robot comes from. H.G. Wells also predicted wireless phones and jumbotrons in a novel called Things to Come. Robert Heinlein, in an early book, wrote about an answering machine, where you could interpretation of what's actually happening. The automatic ticket machine, where you put in money and get out a ticket. That was Isaac Asimov in the second Foundation series. Virtual reality, of course, is William Gibson. Arthur Clarke came up with satellite communications in 1984, 1945. And then more recently, we get into people who can predict the internet. I mentioned David Brin in his novel Earth, but also Orson Scott Card in what was one of the greatest science fiction novels, Ender's Game, used internet news groups as a vehicle for taking over leadership of the world. There we go. By the way, David Brin also came up with internet searching and global warming in his novel. Those are concepts that now we're left with predictions that haven't come through. Things that science fiction writers came up with are tractor beams, force fields, large-scale nanotechnology. I know that sounds like a non-sequitur, but I think it's a better way to say it. We'll get to it later. Time travel, faster than light travel, and a large slab of stone that radiates weird music and flies to Jupiter. A lot of newer science fiction uses as a starting point singularity, term singularity concept. Now, there's two kinds of singularities. Black hole singularity, with which most people are familiar, and that's a region of space-time where the curvature is infinite. Mass shrinks to mass shrinks to nothing. There's no volume, and yet it has infinite density. This is a hard concept which springs from relativity. The distance of black holes has been proven, and the singularity is at the center. A different concept of singularity, which is central to science fiction, is the technological singularity. By the way, many of you have already heard all this stuff anyway, so you can still hear it. A technological singularity is a hypothetical event occurring when technological progress becomes so rapid that it makes the future after the singularity unpredictable. Okay? Werner Vinge, a science fiction writer, is the one that coined the term. He defined the concept as when computers become self-aware. When computers become super intelligent, that's the tipping point. After that, you can't predict what humans are going to do because human beings aren't going to be running things. It's going to be the super intelligence. Some writers use singularity in a broader way to refer to any radical change in society brought about by new technologies, such as molecular nanotechnology, things like that. And there is also a school of thought that the singularity occurs at some point when technology continues to follow Moore's law. That is, it doesn't level off. In comparison, we travel now about as fast as we've traveled since about 1960, when the first jets came along. That's basically our speed limit for human beings. So in 1960, that ceased to go up. That would just stay the same. The amount we travel increased exponentially. To turn the 20th century, the average person traveled about 200 miles a year, and that was on a lot of trains. Today, people drive with cars and planes an average of 16,000 miles a year. That's an enormous leap. But there is this school of thought that says that Moore's law, and applying it to everything else as well in technology, doesn't have an endpoint, and it doesn't stop growing. It just keeps going. And at some point, it reaches this singularity where things are so different you can no longer predict what's going to happen. This is where science fiction writers they use this as a kind of a jumping off point because it enables science fiction to happen. You don't have to worry about is this going to happen, is it going to happen. You don't have to worry about predicting things. You can just say, sure, it's going to happen. It's going to be a singularity, and we don't know, so I might as well talk about it. Now I want to talk a little about computers because this is a computer science club. Computers, the home computer, of course, came in 1970, 76, 77 with the Apple I, and 1981 with the IBM PC. And since then, it's just been on a complete upward trajectory, both in terms of computing speed, bandwidth, and storage. All these things are necessary to make computers faster and more powerful. but I like to concentrate on one aspect of it, which is kind of central to science fiction themes, and that's computer storage. Because that's where the information is. That's where the databases are. That's where the computer gets the information it uses. And this is fascinating stuff. When I was covering Intel and AMD and people like that in the early 1990s, there was a fear by these companies that they would hit the wall when they got to 40 gigabytes on a hard drive. They just could not shrink it more than that. It wasn't even possible to put more than that. Well, of course, today you can buy a 2, 5 terabyte hard drive and see it on your desktop. And those factors are astronomical when you're talking about the increase in size. I think my first hard drive in 1985 was a 5 megabyte drive, which held everything I needed. There was no Windows, there was no Photoshop, nothing like that. There was just DOS, and DOS didn't take up a lot of space. Today, of course, a good size Photoshop worked over the photos going to take up 5 megabytes. So there's not that's I couldn't even got one of those on my initial hard drive. But let's talk about just pick out a number. Let's talk about 10 terabytes. It's an interesting number. It's enough to hold all the text in the Library of Congress. It's also a megabit for every second of the year. Okay? Now, if you apply compression technology such as DivX, and you have 10 terabytes, you can hold everything that any one of you would see for an entire year, in all your waking, sleeping, bathroom time. All right? Just kind of think of it as a life log. It's a log. Now, why would anybody want to do this? Well, there's good reasons to do it. It would be great, for instance, for everybody from police forces to doctors to be able to have this. If you're a police department and your cops can keep a life log of what's going on, you never have to worry about evidence or because you have it. Similarly, suppose you had a life log of everything you said for a year, and you were getting early Alzheimer's disease. Well, you could go back and search that life log and find out how you responded to questions and how you phrased things over that course of that year, and see how it changed, and see just exactly where your deterioration was. It's kind of neat. The problem with that is that, and this is a problem for all computing these days, is that right now 10 terabytes you can get on a hard drive. You can't get on a flash memory or any kind of more compact and most mechanical kind of device. And if you think about it, where our history really falls apart, when we can start to trace history, is kind of the last quarter of the 20th century. Because that's when people stopped writing things down on books that lasted a long time, started putting them on optical drives, which don't last a long time. In the course of history, they just go away. The stuff just erases itself, decays, it's gone. So you really don't want to think of it in terms of a life log on a hard drive. You want to think of it in terms of something much more stable, much more permanent. Let's think for a second. Let's think about that 10 terabyte number. And I'm going to start to use some numbers that were given out by Charles Stross, who's a British science fiction writer, who wrote a novel called Accelerando. And he's a wonderful writer, and even though he's not a scientist, he gets this stuff. Right now, there are about 80 million people in Germany. Okay? Let's say they all have these life logs. Each one of them is carrying around the ability to record 10 terabytes of data. Okay? Okay. For the entire nation, that's about 10 to 13 bits. It's about 21 to, for a year, you can carry around 10 to 21 bits, and for a century, 10 to the 23rd power. 10 to the 23rd power is itself a fascinating number. It's a very big number. It also happens to be Avogadro's constant. Anybody's familiar with that? Okay. So, there are a lot of examples of what this number means, but if you covered the entire surface of North America in unpopped corn kernels, in order to get enough to make the Avogadro's constant, you need 9 miles deep of kernels. This is a real big number. But it isn't such a huge number when it comes to Moore's law. If Moore's law continues on the rate it's going, it won't be. It'll be achievable very easily. So now the question becomes, how do you store Avogadro's constant if you want to have life logs for everybody? Okay? And this is where science fiction starts to come in, because people start to predict things that, I think of it more as applied science than theoretical science, but they start to look out and say, well, okay, how can we do this? Scientists do it all the time. Science fiction writers do it too. And one of the things that Strauss has posited is the use of a synthetic diamond as a storage device. Synthetic diamonds are pretty cool because carbon occurs naturally in a couple of isotopes, carbon-13, or several, carbon-13, carbon-12, split, often occurring in roughly equal numbers. So what if we had a diamond where we laid it down in molecular levels? This, oh, by the way, this is assuming that Moore's law proceeds to the point where you can have 1 bit of storage, or maybe even 2 in a single atom. Okay, that's kind of the vanishing point. That's theoretically possible. Anything beyond that, we don't know. But we do know on just a physical one-for-one paradigm could work. So what if you lay down strata, molecular strata on a diamond, alternating carbon-13, carbon-12 atoms? You would have the makings of a very, very extensive storage device in a very small space. To achieve Avogadro's constant in a synthetic diamond, you need about 25 grams of diamond. 25 grams of diamond is a cube about 3/4 of an inch up to a side. That's all it is. But it's Avogadro, you get Avogadro's constant out of it. Now, let's see. Here, for all the people in Germany, 25 grams of diamond would store 6 years worth of data. So a little piece of diamond, you've got everything everybody in Germany said and did, or said and saw and heard for a year. That's kind of neat. If you take it a little bit farther, 600 grams of synthetic diamond would be enough to store life logs of everybody on the planet for a year. 60 kilograms, still not very much, would store a life log of the entire human species for a century. That's pretty neat. It's also very large compared to anything we have today, obviously. I think the Google cluster is now running around 5 petabytes of RAM. In memory diamond, you need a microscope to see 5 petabytes. You wouldn't be able to see it. All right. So, computers, the idea that computers can become this powerful. And the storage is just an ancillary to the speed and bandwidth. Brings up one of the great research quests of mankind in the last 50 years, and also one of the primary storytelling primary ingredients for a good science fiction novel, and that's artificial intelligence. Now, a computer is artificially intelligent if it can pass the Turing test. I'll describe that in a minute. An artificially intelligent computer can break down the genomic code, discover new drugs, interpret video, and even predict traffic jams and weather. If it's really intelligent, it could probably clean out your bank account. The Turing test. The Turing test is a test of a machine's ability to demonstrate intelligence. It proceeds, this is the way it proceeds. A human judge engages in a natural language conversation with a human and a machine, and each tries to appear human. Now, everybody's in isolated locations. The judge can't see the computer, can't see the person. So, now, if the judge can't reliably tell if the machine, whether the machine is human, and can't tell the difference between the machine and the human, the machine is said to be to pass the Turing test and assign the order of artificial intelligence. Now the problem, of course, is that this tests intelligence, but it doesn't really test awareness. And that's a big problem. The Turing test doesn't measure awareness, it just measures information processing. In particular, it measures the ability to a computer program to imitate human-like dialogue, which is different than measuring awareness itself. So even if we succeed in creating good AI, we won't necessarily create AA, which is artificial awareness. How does artificial intelligence and artificial awareness make itself known in science fiction? It's primarily through intelligent computers and robots. And robots are key to a lot of science fiction. The science fiction writers assume that the technology is there to create them, so they just use robots. Right? They're necessary to the plot. That's a robot is always a key to the plot because it sets up a situation where people can you can have protagonists, antagonists, and robots as either mediators or one of the other, protagonists or antagonists. We see them in science fiction everywhere. Arthur Clarke had them in 2001. There was HAL, the artificial intelligent computer. Joshua in the 1983 film War Games. And then the robots themselves started appearing in things like Replicants, which is the Blade Runner movie, which was taken from the Philip K. Dick novel, to Android Mutant Electric Sheep. Data in Star Trek, of course, C-3PO, and probably the iconic robot in science fiction is Argandil Olawa, who was the human-appearing robot in the Foundation series of Asimov. It's kind of interesting because Asimov spent almost an entire novel describing the creation of the positronic brain, which was necessary to make this robot. He didn't spend any time at all talking about positronic bones, skin, or hair, which the robot also has to have to look like a human being. He just assumed they could do that. So there you go. Artificial intelligence right now, today, in actual science is kind of on a, it's not at a cusp, it's kind of leading up to the cusp. Researchers at IBM have developed a supercomputer called Watson. Anybody read about it? Okay, Watson is a supercomputer which is going to play Jeopardy. And what makes that interesting is that the computer is not going to be able to just go on Google and find something and spit out an answer based on a simple question. The computer is going to have to come up with ways to solve clever questions in which components of the question are not necessarily directly linked. So, for instance, there could be a question that says, the name of this hat is elementary, my dear contestant. Well, everybody knows it's a deerstalker cat, right? We know that just like the human brain can process that in seconds. I mean, not even seconds. You can immediately hit the buzzer. Deerstalker cat. But it's not quite so easy for the computer, because the computer has to associate the deerstalker hat with a detective who isn't even named in the question. That's tough. And yet this computer has been able to do it. It beats regular Jeopardy contestants that they bring up to our mouth a lot of the time. And I think that this sort of thing, this has a lot to do with language. And language is a big component of artificial intelligence. If the computer can use language, not only talking, but using it, to reason, that does become the kind of tipping point for artificial intelligence. Now there are other much more grandiose and foreboding uses of computers as artificial intelligence as science fiction. The one you know about from watching the Terminator movies is Skynet, which suddenly became self-aware and took over the world. There's another one which I found fascinating. Charles Strauss in Accelerando writes about what he calls a matryoshka brain. Have you heard of that? Matryoshka brain is named after Russian dolls, Matryoshka dolls, which are nested on one side. And Matryoshka brain actually is not, the elements of it are not science fiction as much as science fact. Freeman Dyson, the physicist, came up with an idea for a thing called Dyson spheres. Dyson spheres are concentric circles with spheres inside one another. And in Accelerando, Charles Strauss talks about a Matryoshka brain. Here's how it works. You have the sun, then you break up Mercury, Venus, and you take all the material on those planets and create Dyson spheres around the sun. And you use the energy of the sun to power a computer made out of the matter from those planets. Sounds a little weird, but in fact, it's something that scientists have actually been considering. So it's not a total, off-the-wall kind of deal. The great thing about a Matryoshka brain is that it's so big that it can run basically an entire solar system full of activity. And in fact, in the novel it does. It runs a software called Economy 2.0. And if you aren't on Economy 2.0, you're no place. Another big ingredient of science fiction is nanotechnology. And again, that's something where we're kind of on the leading edge of it, but we're not quite into a practical application of nanotechnology, any kind of skill at all. But if you think forward and think of what's possible by creating machines on a molecular level, you can have the makings of a terrific science fiction. Greg Baer, who was a natural physicist, wrote a book called Slam, in which nanotechnology is used to fabricate weapons. And why not? There's no more, conceivably, it's no more difficult to put, include DNA in nanotechnology than it is anything else. Just to tell the stuff what to do. In William Gibbs's Adoru, nanotechnology is used to make buildings, and the buildings become kind of self-repairing, and they're not aware, but when something goes wrong, they fix it. It's kind of neat. The closet doesn't work, right? Now it works. It's kind of neat. It runs the air conditioning, it runs its own heating system, it runs the elevators, it does everything it has to do. And Neil Stephenson, who I haven't mentioned yet, was a fabulous science fiction writer. He wrote Snow Crash, and more recently a trilogy with very heavy, dense books about history. He wrote a book called The Diamond Age, in which entire residential areas are constructed using nanotech. Taking one step further, Gibson, Baer, and others have written extensively about the confidence of medical science and computer science, where you end up being able to enhance your body. You can do implants, you can change, swap out biological material for non-biological material. These things are really kind of I wouldn't say they're off the wall, but they're not hard to believe. It's just that they're so far away that it's not, you have to kind of accept it. Say, I don't know how they're going to do it, but they're going to do it. That, in turn, is one of the great things about the science fiction writers, is they do come up with these things. It's almost like theoretical physics in that sense. Albert Einstein was not an experimental physicist. He was a theoretical physicist. Instead of taking a bunch of experiments that he'd done and saying, well, what can I put together and theorize from this? We worked it the other way. I have a thought experiment I'm going to use. A guy going on a train, riding up next to a beam of light, and I'm going to use that and work backwards. That's what I think is true. Now, how do we go about proving it? Of course, the great example of that is general relativity theory, which posited that gravity bends light. And of course, how do you prove that, right? Well, you prove it through an eclipse. In 1919, the British astronomer Arthur Eddington did just that. He went to a little island off of South America, and during an eclipse showed that indeed light bent around the sun at precisely the distance that Einstein's theory said would matter. So there's that. So the science fiction writers that's what they do. Most of them, even if they're scientists, are not theoretical scientists. But they put these things out there, which are kind of practical applications of theoretical physics. It's taking what is known now and saying, well, okay, what can we do with this? What could this be? And that I think accounts for why some of these predictions, many of these predictions, come true over time. Okay. Another great theme of science fiction, and one which is actually here now, is virtual reality. William Gibson was kind of the grandfather of this stuff in Neuromancer. We now have virtual reality systems that use everything from medicine to military use to education and to gaming, of course. We're still kind of in the TV stage of that, in the sense that we rely on almost two-dimensional interaction with whatever it is we're experiencing in virtual reality. Where science fiction is taken at is way beyond that. So you have three-dimensional, virtual reality worlds where you are actually in the virtual reality. I think they're next month they're coming out with a remake of Tron, which could be pretty cool. So that's exactly what people are talking about. If I get sucked into the machine, all of a sudden it's inside of virtual reality. In Neuromancer, Gibson sketches out a situation where cyberspace, as he called it, was kind of indistinguishable from real life. Once you were in it, you were in it. And you might know you were in it, or you might not know you were in it. You put your electrodes on your head, the goggles over your eyes, or I think in his case, a jacket thing to his neck, and you dive into a little danger and intrigue where you can be the hero, or you can get your brain fried. Neil Stephenson in Snow Crash, which is his first big novel, created an entire virtual city where a lot of the action takes place. That's kind of neat. I mean, they need a computer to get into it, but once you were in it, you were in it. And since then, there have been kind of a lot of incremental steps forward from that. A newish writer named Joe Haldeman has a book called Old 20th, which is kind of a wonderful paradoxical virtual reality. There's a spaceship going somewhere a long way away. It's going to take a long time. People are going to get bored, so they have this virtual reality system where you can go in virtual reality a couple times a week and enjoy yourself somewhere in the old 20th century. And you go to London during the time of Churchill, or go to World War I in New York during the days of the speakeasy, anything you want. Now, what it turns out, though, is that the virtual reality system is actually running the show. And the people in the spaceship are all in virtual reality, and they don't even know it. And the reason is because everybody back on Earth is dying, and they don't want the people in the spaceship to, freak out about it. So they put them in this virtual reality situation where when they come out of virtual reality, they say, okay, I'm out, I'm going to go back and do what I do, but in fact, they're still in. That's kind of neat. And now we get to the kind of the holy grail, which is faster than light travel. And this is where science and science fiction kind of converge into kind of a mess of theory and ideas of what's possible and what isn't. Captain Kirk just says maximum warp, and that takes care of that. Isaac Asimov in his Foundation series talked about a thing called the jump. And he was talking about hyperspace, which I'll get to in a second. And the jump is simply going from one point in hyperspace to another and then eventually coming back out into real time. It's not quite so easy. The special relativity theory postulates that the speed of light is invariant in inertial frames. That is, it doesn't matter whether I'm coming or going toward or going sideways from a beam of light. It's going to be the same speed every single time. And experimentally, that comes out to 186,000 miles a second. In general relativity, which is the 1915 paper that followed the specific relativity paper, special relativity paper in 1905, Einstein implied it's possible for objects to be moving apart faster than light because of the expansion of the universe. As the farther out you get, the faster things go, and so there's no inertial system that can take that into account. So it's possible. he did, general relativity does say specifically that in a local sense, meaning that two objects passing near each other in a small region of local space-time can't have a velocity greater than light. Now, scientists, not science fiction writers, have kind of seized on general relativity and forced it to postulate a mechanism where you can go faster than light. That's wormholes. This allows traveling between 2 points going through an intervening space. All right, and it works off the general relativity premise that space-time curves. Okay? It curves in back on itself. The problem with that is that it also involves kind of causality problems that general relativity specifically prohibits. So it's possible, but it's not the same. Now, according to theory of relativity, time travel is really easy. You just go forward fast. Right? The faster you go towards the speed of light, time slows down for you, you get back to Earth, and your brother's 25 years old. Of course, in real life, that you move way too slow for that to happen. I think I read where if you spend all your time on airplanes, over the course of your entire lifetime, you would be traveling faster than everybody else, so relativity would have an effect, but the effect would be so small that it would be in the order of 10,000th of a second. And it's probably not worth eating airplane food for your entire life, just to get that much younger than your brother. Now, okay, so, but if you have faster than light travel, if you want to have faster than light travel, there are other ways to get there. One of the most intriguing ones used by a lot of science fiction writers is quantum non-locality, quantum mechanics, where particles kind of instantly teleport across vast distances. And the way it works is that in measuring an object, you're inextricably linked to another object in this quantum state, or spin, where when you perform an alteration on one particle, it affects the other particle as well. It doesn't matter how far those particles are separated. And that's the premise for quantum non-locality, or being able to shoot across vast distances in no time at all. One of the biggest proponents of that is a guy named Robert Sawyer, who's a Canadian science fiction writer, wrote a book called Hominids, in which two parallel universes kind of fall together. In one universe, Neanderthals took over from Homo sapiens, and the other was us. And the Neanderthal physicist is experimenting next to the other in a coal mine in Idaho. So, it all depends on the quantum computing to make that happen. That's fascinating. Hyperspace. Hyperspace is a big thing in science. It's the almost universal now way of explaining faster than light travel. What hyperspace, I think you can define generally as, it means the existence of a separate adjacent dimension, not a universe, a dimension, where you travel outside the normal dimensions, in a separate dimension, and then you kick back into the dimension, real dimension. According to all hard science, the only way to get one place together is a straight path from point A to point B. And hyperspace kind of dispenses with that. You don't need that anymore. The explanations for what can happen, they vary. Hyperspace can be smaller, maybe it's smaller than real space, and therefore the starship's propulsion seems to be greatly multiplied. Or maybe the speed of light in hyperspace isn't a barrier as it is in real space. We don't know. Whatever the reason, the general effect is that ships traveling in hyperspace seem to have broken the speed during their destinations much more quickly, with or without the jumps that Isaac Asimov had, than the theory of relativity would suggest. But hyperspace has become so universal that it's a term that is a given in science fiction today. From Star Wars to again to Asimov to any space opera that you read, science fiction that takes place thousands of stars later. So, is hyperspace a gimmick? Does it constitute legitimate theoretical physics based on some hard theories? That's difficult to say, of course, but the interesting thing is that what we've seen now in the last generation is science fiction writers taking science and turning it upside down and using science as a basis for more science fiction. That's kind of a newish thing. Jules Verne didn't really do that to an extent. He just worked on what was available in terms of practical approaches to life and extrapolated out what they might become. But today you have this whole field of science fiction writers who are hard scientists who are looking at what other theoretical physicists have said and trying to take, build on that and say, okay, well, if that can work, how would it work? What could we have? Since Einstein upended the world in Newtonian mechanics, physicists have been wrestling with a paradox, and it's a wonderful paradox. Relativity, the general theory of relativity, holds that speed and space and time are not absolute. They're dependent. I'm almost done here. They're dependent on the position of the observer in an inertial framework. So, for instance, a rod may be actually measured at different lengths depending on where you are in relation to the rod and how fast you're going. If space and time are not absolute, how can the speed of light be absolute? That's a paradox. It doesn't make any sense. And yet there it is. And to date, no one has been able to come up with a better theory. So, theory of relativity had these special theory of relativity, which kind of cemented the speed of light, which is holding. Now, many of the breakthroughs in physics in the past century seem at first, the time they were made, more science fiction than fact. I mean, that's obvious. Jules Verne, Jules Verne has so many reasons to move when you say science fiction. But conversely, much of what science fiction writers have been positing for the past centuries turned out to be achievable. So the point is, I think, that in science, as in all human endeavors, dreams really can come true. And that's 45 minutes.